Okay, in the last video, when we ran through this example, we showed that if we have this vector field here, the line integral along a positively oriented simple closed curve enclosing the origin of any simple closed curve of that type will be equal to the same the line integral over this little circle, which basically shows that any such curve will have the same any line integral along any such curve satisfying that criteria will have the same value. What we still needed to show was that the line integral along this curve C prime here was equal to 2 pi. So in order to do that, we assume that the circle was small enough to fit inside this curve. Let's call its radius A. Okay, so if its radius is A, then C prime has the parametrization x equals A cosine of t, y equals A sine of t, and t is going to go from 0 to 2 pi. Okay, so now setting up our line integral along this C prime here of f dot dr. Remember, this is the same thing as the line integral from 0 to 2 pi. That's our interval for our parameter interval of f of r of t dot r prime of t dt. Okay, now we're substituting our parametrization into the vector field here, and we're dotting that with r prime of t. So in order to get r prime of t, we're going to need from this parametrization here dx dt, and dy dt. So let me actually sneak those in here. Dx is going to equal, or sorry, just dx and dy. I don't know why I said dx dt, dy dt. Negative a sine of t dy is going to equal a cosine of t, and both of these have a dt attached. Okay, so making all of the substitutions, we're going to get this, and this is straight out of your book, this example. I just really like this example, which is why I want to do it. So after some simplification, we're going to get this. A cosine of t all over a squared cosine squared of t plus a squared sine squared of t. Okay, now if you look at this, this numerator is actually going to be exactly equal to our denominator. We're going to end up with a squared sine squared plus a squared cosine squared, which is the same thing as what we have down here. So this whole thing goes down to 0, the integral from 0 to 2 pi of just dt, which we know is equal to 2 pi. Okay, so that's what we were looking for. To wrap up this section, the last thing I want to do is go back to 16.3 where we talked about this theorem concerning conservative vector fields. We said that we were going to defer the proof of this theorem until we had Green's theorem in 16.4, because that's what makes this proof possible. So again, if you don't remember what that theorem said, we were assuming that we have a vector field on an open simply connected region D, and that the vector field takes this form, f equals pi plus qj. P and q are also assumed to have continuous first order partial derivatives, and that this differential equation holds. So in under those conditions, the theorem states that if all of this is true, then f is a conservative vector field. So now to show that, what we're going to do is let C be any simple closed path in D, and R is going to be the region that's enclosed by C. So if this is D here, remember D is open, and C is any simple closed curve this, and we're going to call R the region inside C, but the simple closed curve is contained in this region D here. Then using Green's theorem, we can apply Green's theorem along this positively oriented curve here, C, so that the line integral f dot dr, which is the same thing as this, can, according to Green's theorem, will become the double integral over r of the partial derivative of q with respect to x minus the partial derivative of p with respect to y. Remember, the assumption that we were making was that these partial derivatives are equal to each other. Well, those are the same partial derivatives showing up in the double integral side of Green's theorem, so the difference between them would be 0, making this equal to 0. Okay, now this C here was chosen arbitrarily as long as it lies in D. So basically what that shows is that for any simple closed curve in D, the line integral of f dot dr along that curve C is equal to 0. And we know that the implication of that from 16.3 is that this line integral is independent of path. So what that implies, based on one of the other theorems that we did prove in that section, is that f is a conservative vector field. So really the reason we needed Green's theorem was to turn this line integral into this double integral, which we had made an assumption about the terms in this integrand, that they were equal to each other. That's what gave us the 0 that we needed in order to invoke that other theorem. Okay, Green's theorem is a really important theorem. It may be I don't know if I'd say it's the most important, but it's definitely up there of the theorems in chapter 16. And we're going to continue working with it in different forms as we proceed through the rest of chapter 16. But this is going to wrap it up for 16.4.